Alrighty, today's video is on heating and cooling curves. So we have talked about phase changes and looking at water. Water goes through heating and cooling, and when it gets heated or cooled, it goes through phase changes. We can graph that by looking at the energy absorbed or heat put in or the amount of time that has passed along with the temperature of the water. So we're going to focus on water, but you could make a heating and cooling curve for any substance as long as you knew the boiling temperature and the freezing point. So for water, we're going to start out at negative 20 degrees Celsius. We're going to say that we're putting energy in, which is heat, or time has gone by. Any one of these three variables on your x-axis, you'll end up with the same looking graph. Water at negative 20 degrees Celsius is a solid. As I put in heat energy, my water stays in its ice form, but it slowly increases in temperature as I heat it. So eventually it goes from negative 20 up to 0 degrees Celsius. Then at 0 degrees Celsius, my water begins to melt, but it doesn't melt like that, right? It goes through a process of a phase change and it slowly melts, staying continuously at 0 degrees Celsius. And that takes a little bit of time. We'll eventually calculate exactly how much time it takes, but for right now, it just takes a small amount of time. So during that time, it stays at 0 degrees Celsius. So we stay at this flat line of 0 degrees Celsius, and that's where it melts. Then once we've gotten here, everything has become liquid water. And again, now as I'm adding in my heat energy, I can start to increase my temperature, and it's going to increase until I get to my boiling point of 100. So I can increase until I get to 100 degrees Celsius. We know that at 100 degrees Celsius, water boils. So just like it being a flat line with no temperature change when it melted, same thing happens when it boils. So again, here when it boils, it stays at a flat line. It takes more energy to boil something than it does to melt something. So this line's a little bit longer. And again, this is an equilibrium. We're going from liquid to gas. So here it's all liquid. Finally, when we get to here, it becomes all gas. Once it's gone to completely gas, then again, it can start to increase in temperature. And it goes just continuously up. Okay, and we'll stop ours here. So we can label our different parts. And initially in this section here, this is a solid. Then it melts. Then we have our liquid. Then it evaporates. And then it's a gas. Remember that temperature is a measurement of how fast the particles are moving. And it's associated with the kinetic energy of the particles. So when temperature is changing, temperature is a measurement of particle energy and kinetic energy. So while I have a change in temperature, I have a change in kinetic energy, Ke. When my temperature stays constant, I'm going through a phase change, then I have a change in potential energy. My molecules are spreading apart or getting closer together. So my change in potential, my molecules are spreading apart. Then while I'm at a liquid, I'm increasing in temperature. My molecules are moving faster, but staying in the liquid state. So that's a change in kinetic energy. When I get up to 100 degrees Celsius, it begins to evaporate. That's a phase change. My temperature stays constant, but my molecules are spreading further apart. So this is a change in potential energy. And then when I become a gas, I again have a change in kinetic energy. On these phase change lines, so both here on my phase change line and here on my phase change line, my system of water is at equilibrium. That means that both phases are present. So in my first one, I have both solid and liquid, or my second one, I have both liquid and gas. Right? They're both present at the same time. I have much more gas here than I do here, but at the same time, there's both gas and liquid happening simultaneously. We can do the same thing as a cooling curve, except it's going to go in the opposite direction. So in this case, I'm going to start at 120 degrees Celsius, and I'm going to cool my water down to negative 20. At 120 degrees Celsius, I start at a gas. We know that gases are going to decrease in temperature until it gets to 100 degrees Celsius. Oh, and I should add that this is the boiling point, and this is the melting point. So melting point at 0 degrees Celsius, boiling point at 100 degrees Celsius. So for my cooling curve, starting at 100 degrees Celsius, I'm going to decrease, because now instead of it being energy absorbed, it's energy released, or it's being cooled, or time. So I'm decreasing until I get to 100 degrees Celsius. So I decrease until I get to 100. At 100 degrees Celsius, I go through my phase change. We know that takes a little bit longer. Then after my phase change, I can decrease until I get to 0 degrees Celsius. At 0 degrees Celsius, I freeze, and then I decrease again to my negative 20. So notice that this graph is the opposite of this graph, or almost like the mirror image, except for my big lines, right? There's a much larger line at my boiling and condensing point than my melting or freezing point, because it just takes more energy. The molecules are at a higher energy state here. So we can label our parts just like before. We have gas, and then it condenses. And then I have liquid, and then we freeze, and then I have a solid. Just like before, we have our freezing point and our condensing point. And you'll notice that my condensing point and my boiling point are both at 100 degrees Celsius. It doesn't matter which direction I'm going in, that's going to happen at the same temperature. Same thing with my freezing point and my melting point. Water freezes and melts at the same temperature at 0 degrees Celsius, because it's in this equilibrium between solid and liquid, and here, equilibrium between liquid and gas. We can add in our changes in potential and kinetic energy. Same thing. If there's a temperature change, there's a change in kinetic energy, because temperature is a measurement of the kinetic energy or movement of my molecules. If there's a phase change, my molecules are either spreading further apart, or in my cooling curve, they're getting closer together. And that is a change in the potential energy. Cooling, going down this direction, I am decreasing in the energy of my molecules. Therefore, this is exothermic. For my heating curve, I am increasing in the energy of my molecules. They're becoming higher energy. Therefore, a heating curve is endothermic. And I think that's everything we need to have. So we have our solid, liquid, gas, our change in potential energy or change in kinetic energy, endothermic and exothermic, and all of our phase changes. Good. So you want to be able to sketch one of these out, and we're going to use these to do calculations. A couple more things to note is the difference between temperature and heat. So I kind of talked about it a little bit previously at the beginning of this video, but let's just go ahead and write down some definitions. So temperature, like I said, is the average kinetic energy of the molecules in a sample. So temperature is a measurement of how fast the molecules move. Okay, it's a V. V. Absolute zero is the temperature at which molecules stop moving. Absolute zero is on the Kelvin scale of 0 Kelvin. So Kelvin scale, Kelvin, that is where the temperature scale of Kelvin is based off of how fast the molecules move. So at 0 Kelvin, they would stop moving. There's a little research that's come out in the last couple of years that says we could get to minus 0.0000000 Kelvin. And if we can get further than that, that's going to change that system. But for now, we're going to go with that at 0 Kelvin, it stops. Heat, the difference between heat and temperature. Heat is a form of energy, either in J, which is joules, or kJ, which is kilojoules. We know that there is 1,000 joules in 1 kilojoule. And energy is what flows between two samples of matter. Energy can either be kinetic, which we said was movement, or potential, which is spacing. And so when we're adding in heat during this entire time, I'm adding in heat energy as kinetic. It's being translated as kinetic energy, and then potential, kinetic, potential, kinetic. It can't be kinetic and potential at the same time. Only one or the other can be changing at a time.